is equal to mu sub 0 over 4 pi times q v cross r hat over r squared. Okay, and that's what do you call it? Log units of r for a single point charge moving at a speed v. You solve for the magnetic field created in a particular location. So, before we do that, let's draw the xy coordinate system. Here's x, here's y, here's z. And we've got a point charge right in the center, and it's traveling along the positive y, in the positive y direction. So using the right-hand rule, okay, so x is equal to 0, y is equal to negative 0.5, so call that right here. And the units here are meters. And z is equal to 0.5, so an equal distance up here. So we're interested in the value of the magnetic field at this position. You agree with that? Okay, so it's in the it's at a position that's in the YZ plane, and it's we can figure out that distance using the Pythagorean theorem, how far away it is, and that would be r in our equation. R hat is going to be a unit vector that points in that direction, right? We can figure that out. We know v, we know q, we know that's a constant. So we've got everything we need to go ahead and figure this out. By the way, it's going to be it's going to be oriented in the x direction. So this will be v. It will be coming out of the board. I don't know if the size of it is yet, but I know that much. Okay, does that kind of make sense to you? Because if you use the right-hand rule, this version of the right-hand rule, your thumb points in the direction of positive charge will move, and your fingers curl in the direction of the magnetic field. Now, usually you think of it, as being exactly in the plane of the charge, but actually, if you rotate this way, magnetic field magnitude is going to decrease towards 0. If you rotate this way, it's going to decrease towards 0. It's going to be maximum right here. Is that going to make sense? Okay, so go ahead and do this. So let's bring the use of 0 q over 4 pi. Let's just bring all that stuff out front. And then what we have to do is 4 pi r squared. Bring that out front. V cross r hat. That's kind of a bring one of the words out. How do you like that? You know what this angle is going to be? It's going to be 45. Do we even need that? Let's just do it. Okay, so let's do the D cross. Let's find r hat over r first. R hat is going to be
r over r squared.
Over
R squared.
the magnitude of r, right? Okay. So what's that going to be? That's going to be x equals 0, y equals negative 1/2 meters, and that would be in the j hat direction, plus 1/2 units cancel top and bottom, which is what you expect. So let's see, 1/2 squared is 1/4, 1/4 and 1/4 is 1/2. The square root of 1/2 will be 1 over the square root of 2. Square root of 2 comes up top, so we get square root of 2 times the quantity negative 1/2 meters j hat plus 1/2 meters k hat. So we can factor that out. Let's do that. We'll have the square root of 2 over 2, which is just 1 over the square root of 2 times the quantity negative, unless have the units there, negative j hat plus k hat. So this is R. That's the unit radial vector. Does that make sense? Okay, so we need that value. That goes in here. And we already know V, so let's go ahead and do this part. V cross, let's just do V cross R hat. So V cross R hat is going to be 8 times 10 to the 6th over there, meters per second. And I'm going to bring the this constant out and multiply it by that constant there. So somebody, what is well, we'll just write it like this: 8 over the square root of 2 times 10 to the 6th. And then those units, meters per second times these units, meters, are going to give you meters squared per second. And then all that's left behind to take the cross product of is J crossed with negative J plus K hat. You agree with that? Okay. So J crossed with negative J has got to be 0. Okay. J crossed with K, what is J? Is that positive I? Yeah. So this equals just 8 over the square root of 2 times 10 to the 6th meters squared per second. I hat. Okay, so it's definitely in the I hat direction, which is what we expected. So we've basically done the hard mathematical part, the part that had a vector associated with it, which is going to be the hard part. And then u sub 0 divided by 4 pi, u sub 0 divided by 4 pi, get rid of this and bring this question. No? Okay, so V is going to be equal to u sub 0 divided by what? It's just going to be 10 to the minus 7 Teslas meters per amp. And then Q over R squared, that's going to be 6 times 10 to the minus 6 coulombs divided by, what is, well, we need to figure out R squared. R squared is equal to 0.5 squared plus 0.5 squared. 1/4 plus 1/4, which is 1/2. And units will be meters squared. Agreed? So we've got R squared. So it's Q over R squared. That's 1 over 2 meters squared. And then we have to multiply that by V cross R hat, which we found to be this. So this times, I'm going to write it in this way, 8 over the square root of 2 times 10 to the 6th meters squared per second. And the units, or I'm sorry, the unit vectors I have. So let's see, this comes up top, and you have a 12. 12 times 8 is, what is that, 96? Somebody do this for me. 96 divided by the square root of 2. 96 divided by the square root of 2 is 96 divided by 1.41.
96. It's gonna be 67.8.
67.8.
Yeah.
Okay, 67.8 times 10. Okay, 10 to the minus 7 times 10 to the minus 6 is 10 to the minus 13 times 10 to the 6, so that's back to 10 to the minus 7. So that's 10 to the minus 7. And the units, let's see, each meter squared cancel with each meter squared. A coulomb per second is an amp, so an amp divided by an amp. Wait a minute. What's going on here? I'm left with an additional, we need to add Teslas, I'm left with a Tesla meter. No, I shouldn't, no, there shouldn't be that there. That shouldn't be there. Why not?
That's because you factored out an
This should have been gone. This is gone, this is gone, because they canceled top and bottom, here and here, gone, sorry. Okay, so this should not be here, so, meters squared, cancel with these meters squared, coulomb per second is an amp, divided by amp is just 1, so you're left with units of Teslas, which is going to be 1. So you get 6.78 micro Teslas in the iPad direction. That should be the value of the magnetic field at that location due to that moving direction. Question? Yeah.
Where did we get the 10 to the negative 6?
10 to the minus 7. That's mu sub 0 is, so it's the value of lum. Yeah. So it's going up the positive, v sub 0 is going up the positive x direction. Okay, so I'm going to draw that over here. So here's the x direction, here's the y direction, here's the z direction. And the wire is oriented in this direction along the y-axis, and the current is moving in the negative y direction. Right? And there is a external magnetic field, V sub 0, that is oriented in the x direction, positive x direction, everywhere. Good? So we've got that, and then okay, it's 8 amps. So you chose V, so x is equal to 1 meter and z is equal to 0. Why don't they give you a y value? I guess it doesn't matter because the y value is it's all 100%. Okay, so that makes sense. Okay, yeah. Okay, using the right hand rule, what direction? At this location, at x equals 1. So let's say that's right here, 1. And here the units are meters. And y equals 0. I'm sorry, z equals 0. So you're right on the x-axis, and you're in the yz plane. I'm sorry, the x y plane, right? Where z is equal to 0. That's only true in the x and y plane. So in this plane, and at a distance of 1 meter in the x direction, everywhere from this wire. So that represents a line that parallels the wire. Going toward y equals positive infinity and y equals negative infinity, right? So all along here, the magnetic field, both through the wire and this external source, has the same value, right? Okay, can you tell me, knowing the direction of the current flow, what is it, an 8 amp current? Can you tell me the direction of the magnetic field just due to the wire? You should be able to tell me. Say again. So you want to use the right hand rule. But which one? This one. And what direction does your thumb have to point? In the direction of the current, right? In the negative y direction. So the magnetic field is circulating, coming out of the plane of the board, circulating around, going back into the plane of the board, coming out of the plane of the board below the current carrying wire, circulating around and going back into the plane of the board above the wire. Agreed? So at this location in the x, y plane, can you tell me the direction of that? Correct. In the positive z direction. Agreed? Okay. So the magnetic field generated just by the wire should be oriented this way. We'll call that VW for the wire. So what we have to do now is figure out the size of this, and we were given the size of this one, and they're perpendicular to each other, so you can just add them together as you add vectors. But in this case, since they're perpendicular, you use the Pythagorean theorem. Agreed? Okay. So VW, the magnitude of it should be equal to mu sub 0 times the current divided by, is it 2 pi times r? Yeah. Okay. So mu sub 0 over 2 pi will be 2 times 10 to the minus 7 Teslas meters per amp. And then I is 8 amps. We divide that by R, which is the distance from the wire out to this point, which is just 1 meter. So the amps cancel, the meters cancel, you're left with Teslas. That's good. You've got 16 times 10 to the minus 7, or 1.6 micro Teslas. And the direction at that particular location is the k hat, or the z direction. So this is V due to the wire. Good? Now V due to the, just that external source, what was that one? What was V sub 0? Okay. So it's 1.5 microteslas in the I hat direction. So if you add these together, which is what you want to do, to find the total magnetic field, it's just going to be 1.5 I hat plus 1.6 k hat micro Teslas. So that would be the answer. Say that again.
No, we have to give the direction to these two, right? Like a vector form?
Well, this is a rectangular format. If you wanted to give it, are they asking for a polar format? The polar format is what you're talking about. If you give an angle and a magnitude, are they asking for that?
That's for magnitude and direction. That's what it
Oh, so they do want what you're saying. If they want the magnitude and direction, that's polar. So what do? Well, we can find the magnitude easy enough. Just 1.5 squared plus 1.6 squared square rooted, right? Use the Pythagorean theorem. And somebody do that and tell me what you end up with.
2.19.
2.19. So the other format is 2.19 microteslas. And then you have to give an angle. Now, you've got a vector going this way and a vector going this way. So the net vector is going to be oriented, I don't know, Okay, this one's a little bit bigger than this one, but not much. So drawing to scale. Okay, so I'm gonna get rid of this one. And this will be the 0, this one. And the resulting vector I'll draw with a different marker, different color. Would be the addition of these two, and would be oriented in this direction, would be B total. Okay, does that make sense to you? Okay, now, the angle, you could express it several different ways, but you want to measure it from the x-axis or from the z-axis. If you measure it from the x-axis, that would be that angle, we'll call it D. D will be equal to the inverse tangent of VW over V0. So that would be 1.6 over 1.5. Somebody mind doing that?
46.8 degrees.
Second,
46.8 degrees.
47 degrees. So it's 47 degrees above plus x axis plus x axis in I think that's all you have to say. Parallel to x z plane. If you're in 3 dimensions, you have to be careful about the way you express the angle. Does that make sense? And you know, that fully specifies the direction. Problem 2?
Yeah.
Was that the whole thing?
Yeah, the other one was just the other two.
Yeah. So, you know, the
Same thing, but different one.
fields within the atom. In the Bohr model of hydrogen atom, the electron moves in a circular orbit at a radius of 5.3 times 10 to the minus 11 meters with a speed of 2.2 times 10 to the 6 meters per second. If we are viewing the atom in such a way that the electron's orbit is in the plane of the paper with the electron moving clockwise, find the magnitude and direction of the electric and magnetic fields that the electron produces at the location of the nucleus treated as a point. Here's the nucleus, here's the direction of the electron in orbit around the nucleus. Okay, using this version of the right-hand rule, your thumb points in the direction the electron is circulating, and that tells you that the magnetic field in the plane of the board, or in the plane of the orbit of the electron, and inside the orbit is everywhere oriented perpendicularly into the board. Would you agree with that? Does that make sense?
I was having trouble, because I thought you have to use it like this, so it's going out of the board.
But your thumb has to point the direction the electron is supported. Okay? So that leaves your fingers curling in the direction into the board. Everywhere, right? Okay. So right there at the nucleus, let's draw the magnetic field. It's oriented this way. That's the D. N. Right? And we we can calculate the value of that because, didn't we develop an equation for the magnetic field at the center of a current loop? It's kind of like the other one for one straight wire, right? Using 0I divided by 2R. Yeah, so you just don't have an I in it. But that's it. That'll allow you to solve the magnetic field, and it's oriented into the board, right? Now, what about the electric field? Okay. The electric field at that location it averages out to be 0. Okay, why?
Because it's the sun.
Okay, well, if the electron's here, then remember, negative charges are field line sinks, so electric field lines go into them. So the electric field is coming in, so it's pointing radially away from the nucleus, always toward this. So it's kind of like, it's going clockwise. So it's just like, the second hand of a clock going around. So if you average it out across a whole bunch of orbits, then it just averages out to 0 because it's always pointing in some different direction around the circle. But if they want you to answer this question at one specific point in time, then when the electron is at one particular point in the orbit, then the electric field will be pointing toward the electron, away from the nucleus, and the magnetic field created by the motion of the electron will be pointing into the board, along the axis through the center of the orbit and perpendicular to the orbit. And you can calculate its value using this. Now the value of this would be, I'm trying to remember what it is.
1/4 for
So it's 1, 4, 5. The charge on the electron over the board radius squared and pointing radially away from the proton. And here I'm just going to put perpendicular to orbital plane. So that'll allow you to figure out the size of the electric field. This will allow you to figure out the size of the Was that it? Anybody else?
Can we do question 35?
One goes up over the top of the loop. I-1 goes, or I-2 goes down over the top. I-1 takes the high road and I-2 takes the low road. So we want to solve the magnetic field at this point. Okay, well, using this version of the right-hand rule, the current flowing through the top part of the loop is curling down into the plane of the board at this location. So the crosshair be up, and now this one, okay, coming this way is coming out of the plane. Right? So let's consider out of the plane of the board to be positive. So out equals plus, in equals minus. Okay? So B total will be equal to B up plus B down. And that's going to be equal to, let's see, for a full circle, the magnetic field at the center is u sub 0 I divided by 2 r, right? So how about u sub 0 I divided by 4 r, half of a circle, right? So u sub 0 I1 divided by 4 r, where r is the radius of the minus u sub 0 I2 over 4 r. So you can factor out the u sub 0 divided by 4 r. And what you have left behind is I1 minus I2. And that will be out. Okay, if you end up with a negative value, that means that it's actually oriented in, right? Okay, so this is equal. So did I answer the whole question? I can't remember what the question was.
And what if they were both equal correct?
Well, if those are the same, then that equals 0, so there's no magnetic field. They cancel each other. Does that make sense? Who asked that? Good. I think that's all there was to that. Okay, anything else?
28.45.
A solenoid that is 35 centimeters long, contains 450 circular coils, 2 centimeters in diameter, carries a 1.75 amp current. What is the magnetic field at the center of the solenoid? 1 centimeter from the coils. We suppose we will stretch out the coils to make a very long wire carrying the same current as before. What is the magnetic field 1 centimeter from the wire's center? Is it the same as that in part A? Why or why not? Okay. So, give me a favor, give me all that info. The length of the solenoid was what, 35 centimeters? Well,
Contains 450 circular coils.
okay, so N is equal to 415 turns. Yeah.
2 centimeters in diameter.
Okay, so the diameter is 2 centimeters.
And carries a 1.75 amp current.
Okay, so I 1.75. Right? For the first question, what's magnetic field in the solenoid? Right?
Yeah, at the center of the solenoid, 1 centimeter from the coils.
So, we derived this on the board the other day, what is u sub 0 little n times I, right? And little n was all the turn density, and that's the number of turns per length of the coil. Not the length of the wire that makes the coil, but the length of the coil itself. Okay? Everybody know the difference? like if you've got a spring, okay, you measure the length of that spring, that's not the same as the length of the wire that the spring's made out of, right? That's what we're talking about. So this is just the length of the spring, basically. Okay, so we've got that information, so we go ahead and figure out what that is. Let's go ahead and do that, because we want to plug that in here to find the magnetic field. So we got everything on. So that's going to be 0.415 divided by 0.35 meters. Could somebody do that for me? 450 divided by 0.35.
1285.7.
A little louder.
1285.7.
1, 2, 8, 5, 1, 2, 8, 6. 1,286 turns per meter. Okay. This thing's a meter long, you have about 1,286 turns. Okay, so that goes in there, and we're ready to go. So it's going to be 4 pi. Use of 0 is 4 pi times 10 to the minus 7 Teslas meters per amp. And now we need to multiply that by little n, which is 1286 turns per meter. So meters go on the bottom of that. And now we have to multiply by I, the current. And the current was 1.75, which would be 7 fourths amps. Now the meters cancel, the amps cancel, you're left with Teslas, that's good, that's what we wanted. This 4 can cancel here, so you're left with 7 pi times 1286. Somebody, what is 7 pi times 1286 times 10 minus 7? What is that?
0.0028.
0.0028?
Yeah.
2.8 milliteslas. So that's the magnetic field in the middle of the solenoid. Okay. And yeah, it's a vector, but it's just oriented, along the length of the solenoid. Was there more to that one?
Suppose we now stretch out the coils to make a very long wire carrying the same current as before. What is the magnetic field 1 centimeter from the wire's center?
Okay, so for a long straight wire, we don't really need to figure out how long the wire actually is. We do have an equation that we derive from log Eos of R for any length wire, but since 1 centimeter is such a tiny distance compared with the overall length, we don't need to worry about using that exact equation. We use the approximate equation for an infinite wire, magnetic field to an infinite wire is mu sub 0 I divided by 2 pi r, where r is your distance away from the wire. Good. And this is going to be definitely within 1% of being absolutely accurate, even though we're not taking into account the actual length of the wire. So, what do we say? 1 centimeter away? Okay, so mu sub 0 divided by 2 pi will be 2 times 10 to the minus 7 Teslas meters per amp. And then we multiply that by the current of 7 fourths amps. And then we divide that by 1/100 per meter. Meter cancel, amps cancel, Teslas. This 100 comes up top, 200, 200 divided by 4 is 50, 50 times 7 is 350. 350 times 10 to the 7th is 3.5 times 10 to the minus 5th. Teslas, which would be 35 microteslas. So D for the corresponding wire, just by itself, it's only 35 microteslas. Do me a favor. What is 2.8 times 10 to the minus 3 divided by 3.5 times 10 to the minus 5? What do you get?
80?
80?
Yeah.
Okay, so this magnifies the magnetic field by a factor of 80, turning it into a coil. Okay, compared with what it would be at the same distance from the wire. You just had it, in straight configuration. Why? Okay, that was the last part of the question. Why is that so? Anybody answer that question? But why? Why is the magnetic field stronger, even though you're the same distance away from the wire, when you've got it in a long straight configuration compared with there's not more wires, same amount of wire. Depends on what it means. The definition of it.
There's more wire in a certain space.
Yeah, the wire in general is closer. Yeah. Okay, yeah, you may be only 1 centimeter away from one piece of the wire when you've got a long straight configuration. But when you've got it coiled up, you've got all that wire carrying the same amount of current much closer, right? Overall. So, yeah, so you get more of the effect. You bunching that wire up. And not only that, the geometric configuration of having all the coils carrying the current in the same direction, is additive. So you get the maximum effect by, that geometry for the current carrying wire. Good? Okay. Anything else? Yeah. 2850. 16 centimeters and 20 centimeters. That's kind of ridiculous. Okay, so the only place where it really makes any sense, that question, is part B. Part A and part C, you're outside the torus, right? You're either in the donut hole or outside the donut. Okay, only the middle question, part B, is in between the inner and the outer radius, right? So that's the only place where that equation actually applies that we derived the other day. I can't remember what that equation was. Can somebody tell me for a torus? What was the name? Okay. Well, this is the equation used. They gave you the value of n. They gave you the value of I, right? And the only tricky part here was realizing this equation only applies in between R1 and R2. Because that's the only place where you're actually inside the volume, the working volume of the torus. Does that make sense to everybody? Okay. So part B is the only part that really makes sense to ask. And so you just plug in that value of 16 centimeters, 0.16 meters, and you'll get that. Good? Who asked that? Anything else? Nope. Okay. Well, time for another chapter. Well, you know what? I had a suggestion that maybe I should pick a problem and have you all work it in class. So how about we do that?